On PW Gatewala channel. Till yesterday we have seen lot of different types of CPU scheduling algorithms. We have discussed about FCFS, SJF, SRTF, then we have discussed about priority based scheduling. Now today we are going to discuss one of the most important algorithm called as round robin. Very important one point. Second thing is it is little complicated, not much, little complicated, just because when processes are arriving later, in that case sequence becomes little difficult to understand by normal people who don't practice well. So today we are going to learn that particular technique also, and then of course we are going to learn how to solve the questions quickly also. Okay, so let's begin round robin algorithm. So round robin algorithm scheduling criteria is what? Scheduling criteria is exactly same as FCFS. Whichever process comes first should be scheduled first. Okay, but if we have a process running in the CPU, that process doesn't run in the CPU forever like FCFS. It runs for a specific duration of time. That is called as quantum. Once a process goes for the running CPU in the CPU, that process runs for a quantum time unit, whatever quantum we decide. Then after that it will be preempted and other process comes. Then other like this. So it's something like you guys are playing game of cricket in some, gully cricket, maybe in some kind of small area where you used to play for like 10 balls each or 12 balls or each person will bat like this. So one person, two person, three person, four person, each player will play 2 overs of batting, and then it takes next particular person's turn like this way. If you decide 2 over, again 1, 2, 3, 4 player, then again 1, 2, 3, 4 player like this, it keeps going. That is what round robin scheduling. Okay, so criteria is what? Criteria is arrival time. Whichever process arrives first should be scheduled first, but along with that another criteria is quantum. What is the quantum? Quantum time called as time slice also. I'll write the definition here. What is quantum? Quantum is that duration of time for which a process runs in CPU maximum if it is given to run. After that, process definitely will be preempted as soon as quantum is over. So quantum is that maximum amount of time for which a process runs on CPU at once, and after that it will be preempted, which means the type of algorithm is definitely preemptive algorithm. Okay, you guys have heard about this algorithm before? Can you please type down in the comment box? Subrata, Ghosh, Mahesh, hello, good evening. Other members also who are watching silently. Did you ever see this algorithm before? Okay, now we have a very simple question here. 4 processes, their arrival times all 0, burst times given, quantum is 2. If we will solve this question, this is very easy one. Let's draw the Gantt chart. First of all, at time 0, we have all processes arrived. If at time 0 all processes arrived, based on arrival time, I'll have to schedule the processes, but the processes are having equal arrival time. So based on their IDs, of course, FCFS says if arrival time equal, go with ID. So based on IDs, I will add all the processes in ready queue like this. So P1, then P2, then P3, then P4. Like this, you will add the processes. First process we will run is P1. See, P1 takes total 3 unit of time to run, but we will not run P1 for entire 3 unit of time. No, we will run P1 for only quantum duration 2 and preempted. So if quantum duration 2 P1 runs, remaining is just 1. Next is, in the queue, next turn is what? P2. So next is P2, P2 will run next. When P2 runs next, remaining is 4, up to 2 time unit only P2 runs. That is the quantum effect of quantum. Next sequence, in the sequence we have next process is P3. So P3 runs next, up to 6 time unit, remaining is 2. In the next sequence, P4 is there. So P4 runs next, 2 time unit up to 8, the remaining is 3. Now again P1 runs up to 9, remaining is nothing. Now you will say, sir, if quantum is 2, why aren't you running P1 for 2 time unit? See buddy, if you play the game of cricket, we decided that each player will get 12 balls to play. If that fellow gets out before that, after playing 6 balls, player got out, will you still ball to that fellow and say, okay, you play total 12 balls? No, out means out, gone. Same thing here. If quantum is 2, that means if a process is given to run on CPU, that process will run for maximum that time. If process needs lesser time, okay, process will leave the CPU. If process needs more time, then we will ask process to leave the CPU forcefully. Preemption happens. So a process cannot run more than quantum, but can run lesser than quantum if process wants to. Here process wants to run only 1 time unit, running and leaving the CPU, done. Next, P2 runs next, 2 time unit up to 11, remaining is 2. Then P3 runs next, up to 13, remaining nothing. Then P4 runs next, 15, remaining 1. Then P1, P3 gone, only P2 and P4 remaining. P2 runs 2 time units, 17. And then at the end, P4 runs 18. Done. Total 18 time unit required. 6 plus 4, 10, 5, 15 plus 3, 18. Yes, total 18 time required. This is what the Gantt chart is. Kindly confirm in the comment box if you guys are okay with this concept. If you guys are okay, then we'll go for the next type of concept, which is actual round robin. See, this is round robin, but easy when all processes arrive together. When all processes arrive together, then it is easy. But when all processes are not arriving together, we have later arriving processes. Arrival time of processes are different. In that case, round robin algorithm is little different. So if you guys are okay with this basic concept, processes will run one by one for only 2 duration maximum. If process finished, done. If not, then preempted, so that next process gets the turn. Same thing happens again and again. Sequence we have written here in the ready queue. Okay, now we are going to have this question. This particular question is having 4 processes, 1, 2, 3, 4, P1, P2, P3, P4. Arrival times are different, 1, 2, 3, 0, 1, 2, 3. And these are the burst time. Now, this is what the type of question you guys will have to learn how to solve. Okay, simple. So let's start with the Gantt chart. Okay, now again, from a very simple, game of cricket, I am taking a very simple example. Let's say you are having a practice for the cricket. So practice of what? Fielding practice, catching practice you are doing. So what you are doing, catching practice means here you have a coach. That particular person is holding a bat and a lot of balls. That coach is throwing the ball in the air like this. All the students, or I should say the learners, okay, the learners are standing in a queue here. 3 students are there. So what happens? The very first person, whoever is standing in the front, that fellow will run forward and will take this catch. Taken. practice done, one catch practice done. Okay, as soon as this particular fellow's catch practice is done, then that fellow will go at the end of the queue and will stand here. Simple. Okay, so currently player number 1 was here, 2 here, 3 here. Player number 1 when went for the catch done, then player number 1 goes back to the end of the queue. So that next turn comes with the player number 2. That is what the basic idea of queue. But let's assume after player number 1 stands here and player number 2 will go for the catching. At that time another player comes, player number 4. If player number 4 comes, where he will stand? You tell me. You tell me when player number 2 gone for catching, player number 3 is next, player number 1 is in the queue at the end. If player number 4 comes, where that fellow will stand? That player number 4 will stand at the end here. Now you tell me, okay, don't tell me lie, okay, you be honest. If you will be on the place of player number 1, will you ask player number 4 that, okay, you come forward ahead of me, I already taken one catch, you take the next catch? No, of course not. If I will be there on player number 1's place, I will stand there only. I will not ask player number 4 that you go ahead. Nah, can't do that. Why? Array, I want to practice more. I want to take more catches. I just don't want to stand in the queue. Right? If I'll get first chance before player number 4, of course I will go. Of course I will go. Yes. So what happens? What happens if any process arrives later? That particular process will be added in the queue later. If any process runs and completes its first burst, okay, what happens? That particular process will be added at the end of the queue, so that we have the sequence always correct. That is what I wanted to explain. Now see, I am going to maintain a ready queue. And this is the time. At time 0, in the ready queue, what process is there? Only P1 is there. Only P1 is there. So, whichever process is available, we will schedule that process, but that process runs only for 2 time unit. 2 time unit it runs, remaining is 4. Boss, when P1 has gone for catching, okay, when P1 has gone for catching, that P1 is not standing in the queue. I removed it in from the queue. There is nobody in the queue. But 0 to 2, when up to 2, P1 was there in execution, is there any other process arrived? From 0 to 2, when P1 was there in the running state, look at this, imagine this, this is the ready state. In the ready state, P1 was only single process, scheduled by scheduler. It is in running state. So it has removed from the ready state. Now, when P1 is in the running, ready queue is empty. 0 to 2, P1 is running. We do have 2 processes arriving between 0 to 2. At time 1, P2 arrives. At time 2, P3 arrives. So when at time 2, P1 is preempted from running state, will be added in the ready state. 2 processes are already there before it. P2 arrives at 1, so I have added it in the queue at 1. P3 arrives at 2, it is added at the end of the queue. Next, P1 is coming back from CPU after completion of one burst or quantum. So P1 we will add at the end of the queue. Always remember, whichever process you are running, if it is preempted because time quantum is over, you add it at the end of the queue. This is what I wanted to explain. Can you please confirm quickly if you understood this? Now there is a confusion. Sir, at time 2, new process also arrives. At time 2, P1 also completes the execution. Why you are adding new process first and P1 at the end? This is the rule. If we have a process preempted, and if we have a process arriving, then we will give the chance to new arriving process first. The current process which is coming back from CPU preempted, it will be added at the end of the ready queue. Good evening, Kishore Babu. Good evening. Now, at time 2, which process is at the front of the queue? Front of the queue, P2 is there. So we will run P2. P2 also runs 2 time unit up to 4, remaining is 3. Now, up to 4, when P2 went for running, removed from the ready queue, in the ready queue, P3 and P1 were there in the sequence. 0 to 4, any other process arrived? Yes. 3. At time 3, P4 arrived. So at time 3, P4 arrived. I have added it in the queue. And then P2 completes its burst. So P2 will be added at the end of the queue. Now the sequence is P3, P1, P4, P2. Next process which is in the queue is P3 in the front. So P3 we will run up to 6 time unit. Remaining is 2. Okay, now see, when there is no any new arriving process, there will not be any sequence change. P3, then P1, then P4, then P2, then again P3, P1, P2, P4, P2, 3, 1, 4, 2. This sequence we will continue. This ready queue maintenance we will do only till where all the processes arrive. Once all the processes have arrived, then you don't have to do such kind of task. So let's run these processes in this sequence. First P3 run, done. Then P1. P1 again runs for 2 time unit, remaining is 2. Then P4 runs 2 time unit up to 10, remaining is just 1. Then P2. P2 runs 2 time unit, remaining is 1 up to 12. Then P3. P3 runs 2 time unit up to 14. Completed. P3 done. Then P1, 2 time unit, 16 completed. Then P4, 1 time unit, 17 completed. Then last P2, 1 time unit, 18 and done. All processes done? Yes. Till 18 time unit, all processes will run. 6 plus 4, 10, 15 and 3, 18. Yes, true. Just check it out. What is the completion here and in the sequence if everything is okay? Here context switch will be so many. As compared to any other algorithm, you will be having lot of context switches. How many switches? 1, 2, 3, 4, 5, 6, 7, 8, 9 context switch occurred over here. In between the processes, how many context switches? How you are counting? P1 runs, switches to P2, 1 context switch, then 2, then 3, then 4, then 5, then 6, then 7, then 8 and 9. 9 context switches occurred over here. Okay, fine. If you guys are having any kind of issue, you can ask. If not, then we'll go for the next question. Okay, for this particular question, I would like to change this quantum. I would like to have quantum is equal to 3. Solve this question. You guys try now. You guys try now. Quantum is 3. Solve this question. Try. If any kind of issue is there, you just ask me. minutes I'll give you. To solve the question, at least try. If any kind of issue you guys are having, just let me know. If anywhere you stuck, let me know. Are you guys able to solve it? Any answer? Anything? You are stuck somewhere? Okay, now at very first place, people used to stuck here. Sir, quantum is 3, but at 0 time, no any process is arriving. At time 0, there is no any process arrived. The very first process arrives at 2, which is P5. Okay. So in the ready state, the ready queue when we maintain, we will have to be very cautious just because processes are not given in the sequence. ID and arrival times are not in the sequence. At time 0, no process arrives. At time 2, very first process P5 arrives. At time 2, only P5 arrives. Okay. So at time 2, when P5 arrives, 0 to 2, what happens? Processor, the CPU will be idle. CPU will not do anything, will remain idle. Now at time 2, P5 arrives, so P5 runs. First place, P5 runs. P5 takes 2 unit of burst time only, so it will run 2 unit of time up to 4 and done. That's it. It doesn't even need complete quantum. So at time unit 4, we will have to check out what all other processes arrived. So between 2 to 4, at 3, P3 arrived. So I am adding P3 in the queue. And at 4, P6 arrived. First process P3, P5 of course completed. So I am not adding it at the end. It is done. Okay. Now P3 arrived, P6 arrived. Fine, P5 completed. Now next is P3. P3 we will run for 3 unit of time up to 7. Remaining is 5. And till 7, when P3 is running, removed from the queue, P6 was the only process waiting. Now till 7 time unit at 4, no, done. 5 time unit P1 arrives, so I have added in the queue. Then at 6 time unit P4 arrives, fine, and at 7 nothing arrives. So these two processes added, and at the end P3 I'll have to add in the queue. Why? Just because P3 completes one burst and will be added at the end. Next, first process in the queue is P6. We will run P6. P6 runs for 3 time unit. It can run, yes, the remaining is 1. 3 time unit up to 10 it runs. When up to 10, P6 runs, removed from the queue, P1 is remaining, P4 is remaining, P3 is remaining, and at time unit 8 P2 comes. At time unit 8 P2 comes, and at 10 P6 is added at the end of the queue. This is the sequence now. Now this formed sequence we will continue. Why? Just because there is no any process arriving new now. So once no any new arriving process we have, we can run this sequence. First is P1. Let's run P1. For 3 time unit, remaining is 3 up to 13. Next process in the sequence is P4. Let's run P4 next. P4 remaining 3 time unit up to 16. Done. P4 removed. Next, P3. P3 we will run for 3 time unit up to 19. Remaining is 2. Next, P2 runs for 3 time unit. Remaining is 4 up to 22. Then P6. P6 runs for 1 time unit 23 and over. So I'll remove P6. It is done. Then P1 again. P1 runs for 3 time unit and it is done. 26. Okay, let me extend this. Next, P4 done. P3. P3 is still remaining. Yes, 2 time unit up to 28. Done. Only P2 remaining now. P2 remaining for 4 time unit. So I'll run P2 first for 3 time unit 31 and then again for 1 time unit 32. You will have to write this P2 2 times like this only. That is why I have given P2's running time little extra so that you guys can understand this concept also. What is the concept? If P2 only process remaining and if it is first running for 3 time unit, just because quantum is 3, there will be a preemption. Another time P2 comes and runs for 1 time unit remaining. Done. Okay, let me see if 32 is the total time. Here 21, 4, 24 plus 2, 26 plus 4 up 28. Okay, साथ 21, 21, 22, 23, 24, 25, 26, 26 और 4, 30. Fine. Till 30 time unit all the processes will run. But why 32 here? Just because we have 2 unit of time idle. So 30 time unit processor or CPU will execute 2 to 32 and 0 to 2 no any process is there. That's why idle. Total 32. This is the Gantt chart, number of context switch, etc. You can easily calculate how many context switch is there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. 11 number of switches. Here there is no any switch. CPU was not doing anything. Process to process switch is starting from 4, P5 to P3. Thank you, Anup. Thank you so much. Just see if you guys are okay with this concept and everything is clear to you guys, just because the question was little different than the previous one. If you guys are okay, we'll go ahead. We have another question for practice. Oh, big question again. Quantum 2 given. Solve this question. Okay, now see, I am not solving the question forward. Completion time, P1's completion time is 26, P2's 32, P3 28, P4 16, P5 4 and P6 23. Completion time you can easily get it from here. Then turnaround time is completion time minus arrival time. Waiting time is turnaround time minus burst time. All the things are as it is, no any change. The main motive of solving these questions is getting this correct Gantt chart. Once you get the correct Gantt chart, remaining process is same to same, no any change whatsoever. Okay, Chali. Okay, solve this question. I'll give you another 3-4 minutes. Okay, big question it is. You can take 1 minute extra. See, you guys will have to maintain the ready queue. That is the very first thing. If you don't maintain the ready queue, you will not be able to solve the question correctly. You will be stuck somewhere in between. Question is very simple. It's just that whatever method I have explained, you guys will have to apply. If you can apply, it's easy to get the answer also. Okay, I hope you guys have solved at least half or somewhere. Time 0, we have, at time 0, we have two processes arrived, P1 and P2. So at time 0, we have P1 and P2 arrived. Just because their arrival times are same to same, I have added them both together in the queue with P1 first. Why? Just because P1 is having smaller ID. We know that FCFS algorithm is applied over here. If arrival time same, then the process with the smaller ID will be preferred. Okay. Now at time 0, which process is scheduled? The first process in the queue, P1. So P1 is scheduled and runs for 2 time unit. Quantum is 2. So P1 runs for 2 time unit, remaining is 10. Okay. Now till 2 time unit, When P1 has gone for running in CPU, P2 was there in the queue, but other two processes arriving. At time unit 1, P7 arrives, and at time unit 2, P5 arrives. And P1 comes back, got added at the end of the queue. That's how it is. Fine. Now, what is the process which is in the front of the queue? P2 process. So P2 runs next till 4 time unit. 4 time unit P2 runs, remaining is 3. And till 4 time unit, when P2 has gone for running, P7, P5, P1 were there in the ready queue in this sequence. Now till 4, what all other processes arrived? At 3, P3 arrives. At 4, P6 arrives. So P3 and P6 arrived and P2 added at the end of the queue. Next, first process in the queue is P7. So P7 runs next. For 2 time unit 6, remaining is just 5. Now till 6 time unit, P5 was there in the queue, P1 was there in the queue, P3 was there in the queue, P6 was there in the queue, P2 was there in the queue, and any other process arrives between 4 to 6. Yes, at 5 P4 arrives. So P4 arrives, and of course P7 will be added at the end of the queue. Now sequence we have got already. Just because no new process is arriving, we can go ahead with this sequence. First process P5. 2 time unit up to 8, remaining is 6. Then P1. 2 time unit till 10, remaining is 8. Then P3. Till 12, remaining is 7. Then P6. Till 14, remaining nothing. So P6 is done. P6 over. Then P2. Till 16. P2 remaining only 1. Then P4. Till 18. P4 remaining is 4. Then P7. 20. Remaining 3. Then again P5. 22. Remaining 4. Then P1. 24. Remaining 6. Then P3. P3 remaining a big 5. 26. Then P6 done. P2 is still remaining. Yes, 1 time unit remaining. 27 and over. So P2 is also done. P2 is over. Let me just extend this. It will become even bigger. Okay, next P4. P4 remaining 4 time unit. It's still. So 29 remaining is 2. Next P7. Till 31, remaining is just 1. Next is P5 again. 4 time unit it is remaining. We'll have to run till 33, remaining is 2. Then P1 again. Till 35, remaining is just 4. Next P3. 37, remaining is 3. Then P6, P2 done. P4 again. P4 is 2 time unit remaining. Just 2 time unit till 39, 2 time done. P4 done. P7, 1 time unit. Okay, let me extend it again. P7, 1 time unit till 40 and P7 is over. Okay, P7 over. Done. Next, P5. P5, 2 time unit, only 42. P5 over. Then next P1 again. A big process it is. Remaining is just 2 now. 44. Then P3. 46. Remaining is just 1. P1 will run 2 time unit till 48. And P3 will run 1 time unit. 49. 2 and 1. All done. Let's confirm once if all processes are running till 49 time unit. So 12 plus 5 17 plus 9 26 plus 6 34 plus 8 42 plus 9 51. Made a mistake somewhere. 12 plus 5 17 plus 9 26 plus 6 32 plus 8 40 plus 9 49. Yes, it is correct. Okay. You just join a Telegram channel. That Telegram channel is this t.me/Vishwadeep sir. This is the Telegram link. As it is, if you will type, you will go over there. Vishwadeep sir PW is the name of the channel, and this is the link or ID. If you will join over there and send me a message, please share the PDF of all these classes. I will share over there if you are not able to get it from somewhere else. Okay. I'll share all the PDFs over there. Okay, so this was the entire question. Like this you will solve. Now, see, the thing is, if you could have taken quantum little bigger, 3 or 4, the number of switches will be little lesser than this. So processes will run little longer and switches will be lesser. So what exactly this quantum will impact on the performance of the system? Should I keep it small, or should I keep it large, or should I keep it some medium, or what? So for that, we need to have 4 different types of values and their comparison with each other. If quantum we will take as very, very small, then what happens? If quantum we will take as somewhat small, not small, very, very small, then what happens? If it is large, then what happens? If it is very, very large, then what happens? See, we did not discuss it in the questions, but certainly when there is a switch from one process to another process, there should be some time taken. Do you agree with this point? When P1 is stopped, another process goes for running in P2. There should be some time taken for this switch for sure. Yes or no? You are agreed with that? Now you just see, let's say this context-wise time is very tiny, very small, no problem. Assuming that a process is running for 5 nanosecond and 0.5 nanosecond is the context switch time. So around 10 times process is running, 0.5 times, 10 times means context switch time is very tiny. 5 nanosecond process is running, 0.5 nanosecond context switch time, then again 5 nanosecond process running, and so on. But if I take 0.001 nanosecond as the quantum, then for 0.001 nanosecond process runs, and then for 0.5 nanosecond process is having switch time, then 0.001 nanosecond switch process runs, then switching time 0.5, which means if quantum is very, very small, process runs for very short duration and switch time is too much, that CPU will spend maximum time in switching only. Process runs this much, switching time this much, process runs this much, switching time this much. This is certainly not a good idea. In this process, running time is very low and switching time is too much for CPU. And hence we can write down over here the conclusion. The conclusion says that CPU's efficiency, or we should say productivity, is almost zero. Why? Just because CPU spends maximum time in context switch only, and process execution time is very, very low. That's why efficiency or productivity of CPU is very low. It is something like I asked you to read books. For operating system, I am asking you to read 3 books. For this same topic, you read this topic from 3 books. You have taken one book from your shelf You have all three books. You have taken from your shelf. You read one word. You close it. You keep that book in the shelf. Bring another book. From that book, you read only single word. Close it. Back to the shelf. Take another book. Sit and read. Open and then read one word only. You are reading from each book one word only. Your progress is not very fast. It's very slow. You are spending more of the time for switching between the books, finding the page, reading the word, and then coming back. So reading the word, actual productive work is very low, and you are spending maximum time in the switching only. That's why CPU spends time maximum in the context switch. Now, the second thing, small. This is preferred. Not very small, but small. And what happens in that case? In this case, boss, the system becomes interactive system. What does it mean by interactive system? The interactive system says process will run for shorter duration and then other process comes, then other process comes and so on. Look at this here. I'll explain here. CPU runs P1. So P1 will run for shorter duration. User will get its response. And then P2 runs for shorter duration. User gets that response also, some response. Then P7, then P5, then P1. Like this, CPU will run each process by quick succession and some kind of response is generated by the execution. User will understand, okay, every process is running and going further. With every process I can interact and I am feeling like all processes are running in parallel. So for each process quickly, CPU will get the response and hence the system becomes more interactive. And this is what preferred. If the quantum becomes larger, what happens? For a large duration, a process runs. So CPU can get one process running for little larger time. User will get response for that process for longer time. For other process, response will be little delayed. So the system will become little lesser interactive. Less interactive. And we will not prefer this also, just because we want to have the system interactive like our computer system, in which we feel like all processes are running in parallel, but not running in parallel, actually running in round robin manner. Quickly switching happens so that we feel like all processes are running in parallel, just because we are getting the response for each process. That's why. Last one is very large. If quantum is very large, let's say quantum I have taken is equal to 12. If in this question quantum is 12, P1 comes first. In 12 quantum, P1 completes at first place only in single quantum. Then P2 comes, completed. Then arrival time, P7 comes. In 12 quantum, P7 also completed. Then next arrival is this, 8 quantum 12 completed. Then next process this, quantum 12 completed. What exactly I am telling you here is process will run on the CPU only one time, no any preemption, and process completed. Isn't it FCFS? This is FCFS. How, sir? Why? See, quantum is as big as the maximum burst time of the process. Hence, a particular process comes to the CPU. Before quantum is over, process burst time is completed and process completed. So in arrival time sequence processes will run. This round robin becomes FCFS. So here I'll write down, if quantum is very large, then round robin algorithm degrades to first come first serve. This is certainly not a preferred option. So preferred option is which one? You choose quantum small. Okay, fine. Okay, what are the advantage of round robin? First of all processes execute one by one, so no starvation, means it's a fair policy. Fairness is there. Each and every process getting the equal chance, better interactiveness, burst time is not required to be known in advance, means practically implemented. For practical, of course, practical usage, we don't know when a particular process is actually completing, when and how much time a process will run. Burst time of a process is not known in advance, and that is not required in round robin. See, it is something like we started playing cricket. 2 over, each player will bat. When the game will get over, there is no any finish time. Whenever we feel like, okay, work is done, done. Or else, whenever somebody's mom comes, game is over. At certain point of that is not decided when the game will get over. That we will play 1 hour or 15 minutes or something. No any deadline at all. That is what here we don't know when the processes will run. Till then, we will keep running processes one by one in the round robin manner. Burst time of processes not known. Hence, that's why it is practically implemented algorithm. Disadvantage. The disadvantage is waiting time and turnaround time of processes are more. Not is, here more. So the what happens exactly? This waiting time and turnaround time increases. Why? Just because processes are keep running till the last. That's why. Can degrade to FCFS if quantum is bigger. These are the two disadvantages, but we don't choose the quantum very big. That's why this particular disadvantage will not be there in our system. And waiting time, turnaround time, we don't care about in the practical scenarios. If a process is waiting for a little longer, I don't care. Until and unless my user is happy, getting the response from all the processes and CPU utilization is good, I don't care about waiting time and turnaround time. So that's not the actual main goal of modern day systems. When modern day systems are designed, this is not the goal to reduce the waiting time and turnaround time. So I'm good to go. Practically we implement this and we are perfectly fine. But if you remember, I told you round robin is not implemented alone. It is implemented with the what? Okay, that you will understand in the next class. In the next class, if I have not told you, I guess, round robin alone is not implemented actually. Round robin is implemented along with the priority scheduling. Yes, so priority and round robin together, these are implemented, and how it is implemented you will understand in the next class. Fine. So today's class is this much only. You guys now can take up the PYQs. Just take up the PYQs of this chapter and you can start solving. But still, if you want to wait, you can wait. There are certain particular type of questions where IO also included in the process execution. How those type of questions are solved, I'll explain you, and then later on you can solve all the questions. But based on directly based on the questions or in these algorithms, you can easily solve the questions. Approximately 70-80% questions are directly based on this. You can easily solve. One type of question still remaining, I'll explain in the next future classes. Then you will be able to solve all 100% type of questions from this CPU scheduling chapter. Okay, thank you so much for joining the lecture. See you again in the next class. Have a great day. Happy learning.